Thank you very much. So it's an honor to be here presenting our findings. I'm Ainhoa García, and I'm going to present our poster about patterns of cortical finding in subjective cognitive decline with data from the FACEHBI cohort. So, subjective cognitive decline is the self-perception of cognitive deficits without impairment on a standardized cognitive test. It has been associated with increased risk of subsequent cognitive impairment and dementia. Different studies have estimated that between 50 and 80% of individuals over 70 years old report some kind of complaint in relation to their cognitive performance. And longitudinal follow-up studies of at least 4 years have estimated that 27% of subjects with SCD convert to mild cognitive impairment and 14% to Alzheimer's disease. Therefore, being able to determine which subjects are at risk of conversion is essential and will allow better implementation of appropriate preventive therapeutic measures. Evidence from magnetic resonance imaging studies shows that neurodegenerative changes are already present years before dementia onset. Thus, examining brain changes in SCD may contribute to identify potential biomarkers at an early stage of Alzheimer's disease. Our aim was to determine patterns of brain cortical atrophy in SCD individuals using a data-driven approach to identify potential biomarkers of future cognitive decline. FACEHBI is a long-term study of cognition, biomarkers, and lifestyle that has been designed upon an innovative symptom-based approach using SCD as target population. We included 147 individuals with SCD from the FACEHBI cohort. For this study, we have included the baseline data from magnetic resonance imaging and PET scans, and also all participants were clinically followed up. The magnetic resonance images used were processed with free surfer to obtain cortical thickness measurements of 68 brain regions, 34 from each hemisphere. To analyze the data, we averaged the measurements of the regions in both hemispheres, and we also used the low variance filter, both methods to reduce the dimensionality of the data. This dimensionality reduction was done to avoid overfitting. When does overfitting occur? If you have too much information about the observed cases, the model overfits this data, capturing their sterilities too well, and it is unable to generalize what it has learned to new observation. And that is what we call overfitting. The low variance filter consists of choosing variables that explain a percentage of the total variance of the model above a threshold that is determined. This allows the dimensionality of the data to be reduced while we are certain that most of the variance in the problem is preserved. Figure 3 shows the cumulative variance explained by the variables of the problem. Studies show that models that explain at least 50% of the total variance of the problem can be accepted. So, as it can be seen in Figure 3, we need at least 9 variables. Figure 4 shows the change in the slope of the previous curve, and it is convenient to set the threshold at some point before the slope falls. So, as indicated with the red line, we took into account the 10 variables with the highest variance in the problem. In this case, the threshold was set at 3%, or in other words, each variable selected explains 3% of the total variance or more. Taking into account the characteristics of the data, the dimensional space obtained by 10 variables is suitable for reducing overfitting, and it will explain 54% of the total variance of the problem. After applying the low variance filter, we have retained cortical thickness measurements from 10 regions that explains 54% of the total variance in the data. Here, in Figure 5, are shown these 10 brain regions whose cortical thickness measures have been used for the cluster analysis. As we can see, regions of the temporal, cingulate, and frontal cortex have been included. There are multiple clustering methods that can be applied to the problem. In this case, we chose the WORD method, which is a hierarchical clustering technique. In Figure 6, we can see the process of how this cluster method works. So, as it is shown, the different clusters at each level are created from the union of the clusters of the lower level. One of the requirements of hierarchical clustering methods is that we must indicate the number of clusters to be obtained. To select this objectively, we use an R function from the NV class library that calculates different indices that choose the most optimal number of clusterings according to different criteria. Figure 7 shows the results obtained. Of these 13 indices, 10 indicated that the most appropriate number of clusters was 3. In figure 8 shows the resulting dendrogram after clustering the individuals in the study. As can be seen, the groups obtained are properly balanced. From the analysis carried out, SCD individuals were divided into 3 different clusters, each one for a regional neuroanatomical subtype. We have compared the cortical thickness measurements of all brain regions between the 3 groups obtained. The results presented are those obtained after correcting for the covariates age, gender, and years of education, and also correcting with Bonferroni for multiple comparisons. We obtained a non-atrophied subtype characterized by a generalized increased cortical thickness compared to the other 2 subtypes. Those regions whose cortical thickness is greater compared to the other 2 subtypes are marked in blue in figure 9. Then, comparing these 2 other subtypes with each other, one of them is characterized by atrophy in the temporal region, as it is shown in red in figure 10, while the other subtype has atrophy in the cingulate and parahippocampal regions, as shown in yellow in figure 10 as well. After finding the regions where atrophy of each subtype occurs, several comparisons between clinical, cognitive, and biomarker variables were carried out between the groups. Results presented in figure 11 are those obtained after using age, gender, and education years as covariates in logistic regression and ANCOVA analysis. We obtained a non-atrophy subtype characterized by younger age in comparison with the temporal and the cingulate subtype. Regarding the temporal subtype, it is characterized by having a worse performance in verbal fluency and processing speed tasks in comparison to the non-atrophy subtype. Finally, we have individuals grouped in a cingulate atrophy subtype with worse scores in verbal fluency tests compared with the non-atrophy subtype. Moreover, although not significant, we have found the cingulate subtype showed higher rates of an MCI conversion during the follow-up. At the time the analysis were carried out, the majority of the participants had finished visit 4, and some of them had already completed visit 5. However, we did not find any significant differences between ApoE, E4, and amyloid deposition, nor in the other variables examined. So in conclusion, in this study, we determined 3 distinct patterns of cortical thinning in SCD individuals. First, a non-atrophy subtype was found, whose individuals didn't show relevant cortical atrophy and were significantly younger compared to subjects of the other 2 subtypes. The other 2 subtypes do show cortical atrophy with respect to the group explained before. When we have compared them with each other, we have seen that one showed atrophy in some temporal regions, while the other showed cingulate and parahippocampal atrophy. If we compare clinical, cognitive, and biomarker variables between the temporal subtype and the non-atrophy subtype, individuals from the temporal subtype showed a lower performance in verbal fluency and processing speed tasks. If the comparisons are between the cingulate subtype and the non-atrophy subtype, individuals in the cingulate subtype were also characterized by worse scores in verbal fluency tests. Furthermore, they showed a greater risk to conversion to MCI compared with the other 2 subtypes. These preliminary findings could show the earliest neuroanatomical changes that may precede future cognitive decline, allowing an early diagnosis and a better implementation of preventive measures. Thank you very much for listening to me.